Yesterday we introduced this way of proving induction, and we looked at it with series because we're working in the series topic. But of course, as I was saying yesterday, it's not necessarily just about series. Induction is a type of proof. It's an idea. We can apply it to other sorts of problems as well. So the next type of one we're going to look at is these divisibility ones. And in this case, I think I even mentioned this one yesterday. Yes, of course it's obvious that if you get three consecutive numbers, they're going to be divisible by 3, because somewhere in that string of 3 numbers, one of those numbers itself must be a multiple of 3. But that's not really good enough for a proof. I mean, it's logical, but we'll prove it by induction. So how do we do that? Well, it's the idea that we're interested in. So the idea was, well, let's prove it for the first case. So the first case, or when n equals 1, so 3 consecutive numbers would be 1 times 2 times 3, which is 6. And yes, 6 is divisible by 3. So in this case, I don't have a left-hand side and a right-hand side. I'm simply saying, oh yeah, that is divisible by 3. So yep, it works for the first one. Now, the next interesting bit is, well, how do I write my assumption then? Okay, so I want to assume it's true for n equals k. The way I do it is I set up like a little equation, if you like, an algebraic statement. If I know it's divisible by 3, then k times k plus 1 times k plus 2 must be equal to 3 times some whole number. So I'll just introduce another pronumeral, capital P. And again, P has to be. So I need to state that in my assumption, and I'm assuming P is a whole number. It's an integer. Okay, so that's going to be my assumption. So I now want to prove it's going to be true for k plus 1 as well. So if I get k plus 1 times k plus 2 times k plus 3, that'll also be 3 times some whole number. But notice, I don't call that one P, because of course that wouldn't be true. They won't both be equal to 3P. They're both 3 times some integer, but they would be different integers you would expect. So this time 3 times just, well, some integer, which I'll call Q. Let's go and prove it. So this is not a series type, so I can't go, oh, sum to k plus 1 is sum to k plus 2 and k plus 1. So I'm just going to write down the statement that I'm trying to prove is a multiple of 3. So there it is, k plus 1, k plus 2, k plus 3. Somehow I've got to get my assumption into that. And my assumption was k times k plus 1 times k plus 2. What I do is I actually expand it out, but not completely. I just expand out that last parenthesis, because I could say, well, that's the same as saying k times k plus 1, k plus 2, plus 3 times k plus 1, k plus 2. And the first one is our assumption, k times k plus 1, k plus 2. So I can say, well, that's 3p. And now, when I look at it, look at that, there's a common factor there of 3. The only thing I have to make sure of course, is the other factor, p plus k plus 1, k plus 2, is in fact a whole number. Well, if we look at it logically, we know P was a whole number because we assumed that. We know K was a whole number, we assume that. Now, if I add 1 to a whole number, I'm going to get a whole number. If I add 2 to a whole number, I'm going to get a whole number. If I multiply 2 whole numbers together, I'm going to get a whole number. And then if I add it to the P, so yes, that would be an integer. So it is fair enough to say, yep, that's equal to 3 times Q. Q in this case would be P plus K plus 1 plus K plus 2, but that would be an integer. So I've got my proof. So hence the result's true for k plus 1, if it's also true for k. And now we can induce it's true for all. So we proved it was true for n equals 1, so by induction then we can induce that, yep, it'll work for 2, it'll work for 3, it'll work for 4, and so on and so on. Let's have a look at another one where we're playing with the powers. These are a little bit more interesting, I think. 3 to the power of 3n plus 2 to the power of n plus 2 is always divisible by 5. So again, well, let's prove it true for the first case. So 1, that would be 3 cubed plus 2 cubed. That turns out to be 35. Yep, 35 is divisible by 5, so we're okay. So that works. So my assumption will be for n equals k. So 3 to the power of 3k plus 2 to the power of k plus 2 is 5p, so 5 times some whole number. I want to assume, sorry, that's what I assume, I want to prove for k plus 1. And so if I sub in k plus 1 for k, I'll get 3 to the power of 3k plus 3 plus 2 to the power of k plus 3. I want to prove that's 5q, where q is some whole number. All right, let's go prove that. So how do I do that? I've got to get the assumption in there. What we tend to do is we substitute the assumption in, but the assumption rearranged. There were two things there. There was 3 to the power of something and 2 to the power of something. So what I'm going to do is I'm going to look at the first one. I'm going to make, in my assumption, the 3 to the power of 3k the subject. And that's what I'll end up substituting in. So when I look at 3 to the power of 3k plus 3, using my index laws, I could rewrite that. Because that would be the same as 3 to the power of 3k times 3 cubed. 3 cubed is, of course, 27. It allows me to sub in the assumption, because that is the assumption rearranged. If you have a look at what we assumed, if I moved the 2 to the power of k plus 2 to the right-hand side, I've got 3 to the power of 3k is that. Now, sometimes when you don't substitute straight into the assumption and you substitute a rearrangement, sometimes we might write a note to the side to make it obvious what we've done there. Subbing in the assumption rearranged or something like that. Okay, we've got to show this is a multiple of 5. Well, the first bit's okay. 5 will go into 135p. I've got minus 27 lots of 2 to the k plus 2 plus 2 to the power of k plus 3. But again, if I make those powers the same, so the 2 to the power of k plus 3, I'll rewrite. I'll make that 2 times 2 to the power of k plus 2. And now, how many 2 to the power of k plus 2's do I have? Well, I've got negative 27 plus 2, which is negative 25, and that is a multiple of 5. So I can now factorise the 5 out. The question is, what I'm left with, is that a whole number? And so if we look at that, we say, well, yeah, p's a whole number, so 27 times p, that would be. K's a whole number, so 2 to the power of a whole number, well, that's always going to give me, yep, that's definitely going to be an integer. There's no way it can't be an integer. That is true. It could be written as 5 times something. So we have our proof. And again, we can now go and induce the proof from there. We know it's true for 1, so by induction it's going to be true for 2, then 3, then 4, and so on. So that's the sort of idea with a divisibility problem. It's not a left-hand side equals right-hand side sort of proof. It's you sort of got to create your own equation or expression that you want to prove in it. All right, well, let's add, it's the same exercise, but now I've pulled out the divisibility ones out of that exercise to have a look at.